Hey guys, this is the High School Scientist and this is a follow-up to my previous video. In this video, I'll be explaining you guys the concept of dot product of two vectors. But yeah, a quick recap, we are using Cartesian coordinate system, which is basically a way of representing a vector as a coordinate. So in this example, one vector is being represented with 3 directions and 3 magnitudes. But you have to understand that these 3 directions, unit vectors, are kind of like constants. So it basically means that these magnitudes are more than enough to represent the direction of any vector. Like the direction of the vectors will change even if one of the magnitude changes. Okay, that was the basic stuff and let's move on to the more important stuff. Hey guys, I just forgot to tell you that this thing which I was just explaining is called a position vector. And this basically means that the origin or the starting point of a vector is fixed, but the end of the vector, the side with the arrow mark, can move when something is added or subtracted to it. So here we have dot product, which is the scalar product of two vectors, and cross product, which is the vector product of two vectors. Yeah, I'm not making this up, these are the actual lines from the textbook. Okay, these topics are really fun to learn and they deserve a video of their own, but just for the purpose of this video and to remind ourselves that we are in a physics class and not in a math class, I would like to just give you an idea of what these are. So dot product is a way of converting two vector values into a single scalar value. It can also be used for finding the angles between two vectors. There are two ways of doing this. One, you can use the Cartesian coordinates, or you can use the vectors directly. But what does this all mean? Like, you would want to know the necessity or the reason behind all these formulas. I get that, and to understand this, we may have to take a deeper dive. Okay, we have a two-dimensional surface, and we can locate any point on the surface just by getting a coordinate. We do need a reference line like the x and y axis, and by using them we can get an exact location of any point on the surface. So this method gives us a way to locate any point on the surface. Now we need a method to reach any point on the surface. And that's where adding and multiplying vectors helps us to reach where we want to reach. And not just that, we have to make it simple enough so that we can actually make use of them in the practical world. And that's why we humans came up with the coordinate system. We have one vector. Now multiplying it with a number or a scalar will help us to reach anywhere on this line. So using a combination of a vector and a scalar gives us an access to this line. Now what if we add or use two such combinations of vectors and scalars? We get access to an entire plane. Because here we can simply change the scalars to help us get to our destination. But this gets even more interesting when we add another or use 3 such combinations. Now we have access to everywhere. So just by using these 3 scalars and vectors, we can describe any path we want in a 3-dimensional world. So this was like pretty easy and basic stuff. And the reason why I wanted you guys to know this is because it's important to understand what's happening in the fundamental level. So yeah, now let's try to understand the topic of this video, the dot product of two vectors. So it basically means how much of two vectors are in the same direction. Okay, let's just work with examples. Here we have two vectors which are generally pointing in the same direction. So the dot product of A and B will be like multiplying the length of projection of B with the length of A. So what this does is it gives us how much of both of these vectors are generally in the same direction. Or more like how much a vector is in the direction of the other. So in this case we'll just use two vectors U and V. So V dot U will be like how much of U is in the same direction as V. Now there is one more thing really interesting here. It doesn't matter in which order they are. It can be U dot V and still the result will be the same. because it would make sense that the amount of u being projected on v will be as same as the amount of v being projected on u, as long as they have the same magnitude. But this is not what's interesting. It doesn't matter how different the magnitudes are, the result is still gonna be the same. Isn't that just amazing? Well, there is also an amazing way to represent this without having the need to use any diagrams. It's because math is just amazing and it gives us patterns to play with. So if you notice, if these vectors are in the same direction, then we can multiply the magnitudes directly because the projection is as same as the actual size of the vector. So basically, if the angle between the vector is 0, then the dot product of those two vectors have the maximum possible value. And just like that, if the vectors are perpendicular, then no matter how large they are, their dot product is going to be 0, as there wouldn't be any projections at all. So when the angle between the two vectors is 90 degrees, then the dot product has the least possible value. It's basically 0, but yeah. Like, do you see the pattern now? It's obvious that the dot product of two vectors depends upon the angle between them. And if you look closely at these values, then you should have noticed that these are exactly the values of cos theta. When the angle between the vectors is 90 degrees, the dot product of those vectors is 0, just like cos 90. And when the angle is 0 or 180 degrees, the dot product is maximum, or kind of like the product of both the magnitudes which are multiplied with 1 or -1, just like cos 0 or cos 180. And it's not just that. These values, the dot product of any two vectors, is directly dependent on the cosine value of the angle between them. So it shouldn't surprise you if I say that the dot product of two vectors, let's say a dot b, can be written as the product of a and b multiplied by the cosine of the angle between them. Such simple things can take so much time to explain, and I like to do that just because it's fun. So I'll continue with the cross product of two vectors in the next video, and also try to work out some examples relating to these topics. Yeah, that's it for this video. This is the High School Scientist signing off.